Okay guys, hello and welcome. So in this lesson of ours, we are going to discuss tutachafua the KCSE 2025 Chemistry Paper 2. Buckle up and let us start. Now on to our first question. Table 1 shows part of the periodic table of elements. Okay, so we have our table over there. And with a few of the elements, mentioned. And as we can clearly see, all of the elements are in period 3, okay? So you can just tell we have period 1 at the very top and then period 2 and period 3. So just a reminder to us, when you have elements belonging to the same period, they share the same number of energy levels. So with these elements being in period 3, that means all of them are going to have 3 energy levels. So for example, magnesium is 2, 8, 2. Okay, so yeah, 3 energy levels. Okay, part A, explain each of the following. Roman 1, atomic radius of the elements decreases from magnesium to chlorine. So essentially, the question needs us to explain why when it comes to the atomic radius, okay, we are going to have magnesium having the largest atomic radius and chlorine having the smallest. Remember, when you're talking about the atomic radius, we are essentially referring to the size of the atom. So the larger the atomic radius, the larger the size of the atom. So out of all of these that you can see, magnesium, aluminium, silicon, phosphorus, sulfur, and chlorine, magnesium is going to have the largest atoms, okay, followed by aluminium and so on, until lastly with chlorine having the smallest out of these. Now, explanation. Why is this so? Why are we talking about them having different sizes of atoms when they all belong to period 3 and therefore they all have the same number of energy levels? So they all have 3 energy levels, but when it comes to the sizes, they are different. Now, let us discuss this. As you can see from the image above, okay, we are also incorporating sodium, but as you can see, we are having the atomic radius decreasing as we are moving from the left to the right, okay, the left being where magnesium is. Sasa, when it comes to the atomic radius, okay, it's tied to the atomic number referring to the number of protons. Now, magnesium has the atomic number of 12, so it has 12 protons. Aluminium has 13, an increase of 1. Silicon 14, phosphorus 15, sulfur 16, and lastly chlorine having 17 protons. So as you can clearly see, what is happening is that as we're moving from magnesium to chlorine, the number of protons increases. And because we are having an increase in the number of protons, we are going to have an increase also in the effective nuclear charge. The force of attraction that is going to be present between, the protons which are present within the nucleus and the electrons is going to be stronger. So the electrons are going to be pulled closer towards the center where the nucleus is, right? And by doing so, we are going to effectively decrease the size of the atom. So chlorine has more protons and therefore a stronger nuclear charge. So this pulls the electrons closer towards the center, therefore the atom becomes smaller. Now I know you are going to have students saying that, but madam, aren't we also having an increase in the number of electrons? And yes, you will be right, because in an atom, the number of protons will always be equal to the number of electrons. So yes, chlorine does have 17 protons. It will also have 17 electrons. But when we talk about the force of attraction, our focus is targeted towards the proton, the atomic number. Therefore, we are going to state that the reason why we are having the atomic radius, decreasing as we're moving from the left to the right is because of the increase in the number of protons. This increases the effective nuclear charge, and therefore it pulls the electrons closer towards the nucleus, and by doing so, it decreases the size of the atom. Okay, I hope that was clear. Now guys, I usually say this. If you feel like I am talking a bit faster than you're used to, just manipulate, just change the playback speed, roll it down, slower to suit your pace. And if you need more time to take in a particular question, you can pause the video, take as much time as you need, and then play it to your heart's content. Haya, tuendelee. To Roman 2, ionization energy of the elements increases from magnesium to chlorine. So we need to explain why. When it comes to the ionization energy, again, we are having an increase from magnesium to chlorine. So essentially, the ionization energy of chlorine is going to be the highest, okay? And magnesium is going to be the lowest. So we need to explain this. But before we do that, let us just start with the basics. What do I mean by ionization energy? I know most of you are going to be aware, but reminding ourselves doesn't hurt, right? So ionization energy refers to the minimum amount of energy that is required to remove an electron, usually a valence electron, from an atom in its gaseous state. Now, when we talk about ionization energy, okay, when we talk about electrons, if you need to remove an electron from an atom, you need energy. Because remember, these electrons are going to be attracted towards the nucleus, okay? So there's going to be a force of attraction between the two. So you need to weaken this force of attraction to such an extent that you can have the removal of an electron. And doing so requires an input of energy. This energy is what we call the ionization energy. Now, we're being told that when it comes to these elements, okay, magnesium has the least ionization energy, while chlorine has the highest. Why? Again, we are coming back to the increase in the atomic number. So the atomic number increases from magnesium to chlorine because we are having an increase in the number of protons. And remember, an increase in the number of protons increases the effective nuclear charge. So by having stronger forces of attraction between the electrons and the protons, you are going to need more energy, okay, in order to remove an electron. So more energy translates to a higher ionization energy. Okay. Proceeding to part B, explain each of the following in terms of structure and bonding. Now, I want to say this. If you look at B, part 1 and 2, they both discuss or they both are related to the melting points. Now, I want to say this. Whenever we discuss or whenever you are asked for the reasoning behind the melting point, the boiling point as such, it's always tied to the type of bond that is present. So if you're being asked, why is the melting point of A, for example, lower than that of B? It's the bonds that are present. Now, you can have some cases, okay, whereby you have A and B having different types of bonds, and therefore with one being weaker than the other. That could be your reasoning. Or you can have a case whereby both A and B have the same type of bond, but the strength differs. You can have the same type of bond, but it can be stronger in one element and weaker in another. As you're going to see in Roman 1. Okay, so Roman 1, the melting point of aluminium is higher than that of magnesium. Aluminium and magnesium are both metals. Metals have metallic bonds, okay? Now, metallic bonds are essentially just based on electrostatic forces of attraction. When we talk about electrostatic forces of attraction, we are talking about a force of attraction that is between particles that are oppositely charged. Okay, for example, in this case, you are going to have a force of attraction between the positively charged nucleus because of the presence of protons and between the negatively charged electrons. So we have two different particles, one positive, the other negative. And because of that, we end up having an electrostatic force of attraction. So this is what constitutes metallic bonds. So I have also included sodium in this discussion of ours. Bear with me. Remember, by the way, we are not here just to tackle the past KCSE question. Yes, that is our main goal, but we are also here for the overall revision of chemistry in general. Now, when we talk about the forces of attraction, okay, it's going to be mostly based on the nucleus of an atom and the delocalized electrons. Now, I want you to look at sodium. Sodium has the electron configuration of 281. So, in total, how many electrons does sodium have? It has 11 electrons, right? It has 11 electrons. It also, therefore, will have 11 protons. So, it's going to have a neutral charge, okay? Because the negative charge of the electrons is going to be cancelled out by the positive charge of the protons. Now, when metallic atoms form a structure, what happens is that their valence electrons become delocalized. Now let's stop there. Tulisema in a sodium atom, you are going to have the electron configuration of 281. 1 being the valence electron. This is the electron that is going to be present in the outermost energy level of the sodium atom. Sodium has 1 valence electron. Now, when the atoms form a metallic structure, what happens is that the valence electrons usually detach, okay, from the atom. Detach, yani kidogo zinajitoa from the atom. They no longer become fixed to the atom, but they now have the ability to move within the structure. As you can clearly see, they are moving within the structure. And this is what we call delocalized electrons. They're not fixed to a certain atom, no. They are capable of moving within the structure. And this is the reason why metals are good conductors of heat and electricity, because of the delocalized electrons that move within the structure. There we go. So as you can see with sodium, sodium has 1 delocalized electron per atom. Okay, this is the one that is donated. Is it donated really? That detaches from an atom. Magnesium has the electron configuration of 282. So it has 2 valence electrons. So that means we're going to have 2 valence electrons from magnesium detaching, becoming delocalized and moving within the structure. Aluminium has 3 delocalized electrons per atom. Just by the look of it, you can already tell that aluminium has so many more delocalized electrons. So yeah, why am I emphasizing the delocalized electrons? Now, when it comes to metallic bonds, metallic bonds are based on electrostatic forces of attraction, where you're going to have a force of attraction between the nucleus that contains the protons that are positively charged, and also between the electrons, specifically the negatively charged delocalized electrons. So if you have more electrons, like in the case of aluminium, the strength of the metallic bonds is going to be much, much stronger, as compared to sodium that has only 1 delocalized electron and magnesium that has 2 delocalized electrons. So how are we going to phrase this? Aluminium has smaller atoms. And yes, kumbuka what we just stated. As you move from the left to the right of the periodic table, you are going to have a decrease in the atomic radius. Okay, so sodium has the largest atoms, followed by magnesium, and then lastly aluminium, which will have the smallest atoms and therefore the smallest atomic radius. Now, the atomic size is also important, because when you have metallic atoms that are small, are those thunderstorms? Okay. Now, when you have metallic atoms that are smaller, they tend to have stronger bonds. So aluminium has smaller atoms with 3 delocalized electrons per atom. Okay, per atom. I need you to emphasize on that. A lot of students usually state it has 3 delocalized electrons, and you just leave it at that. Do you mean that it has 3 delocalized electrons in general, or is it per atom? Compared to magnesium, whose atoms are bigger with only 2 delocalized electrons. So because of this, aluminium is going to have stronger metallic bonds, which require more heat energy to break. Okay. Higher. Moving on to Roman 2. The melting point of phosphorus is higher than that of chlorine. Sawa. Okay. We are still on melting points. Tumesema melting points and boiling points should be tied to the type of bonds that are present. Now, if you look at phosphorus, if you look at chlorine, these are nonmetals. They are molecular compounds. Molecular compounds will have which type of bond? Yeah, you guessed it right. The van der Waals forces of attraction. So phosphorus and chlorine will have the same type of bonds. But clearly, it's stronger in phosphorus than in chlorine, because phosphorus has a higher melting point. So let's discuss the reasoning behind this. Now, both phosphorus and chlorine form molecules. When it comes to chlorine, we are always told chlorine is diatomic. That means the molecule of chlorine consists of 2 chlorine atoms. Okay? covalently bonded to one another. Phosphorus, on the other hand, is going to have a molecule that is tetraatomic. This means that the molecule is going to have 4 phosphorus atoms covalently bonded to one another. Now let's pause there. I am sure someone who's listening will be like, why are you talking about covalent bonds? And you just told us that it's the van der Waals forces of attraction that we are interested in. Yes. Inside of the molecule, you are going to have covalent bonds. So inside of the chlorine molecule, you are going to have chlorine bonded covalently to another chlorine atom. Inside of the phosphorus molecule, you are going to have one phosphorus atom covalently bonded to 3 other phosphorus atoms. Emphasis on inside the molecule. Van der Waals forces are forces of attraction that are present between molecules. So one molecule will be attracted to another molecule by van der Waals forces of attraction. Sasa, they will both have these type of forces, but van der Waals forces, the intensity or the strength of van der Waals forces is usually tied to the size of the molecule. What do we mean by this? The bigger the molecule, the stronger the van der Waals forces. As simple as that. The smaller the molecule, the weaker the van der Waals forces. So in this case, with the phosphorus molecule being larger, automatically that is going to make it have stronger van der Waals forces, which are going to require more heat energy to break. Hence, the higher melting point. Chlorine, on the other hand, the chlorine molecule will be smaller in size because it only contains 2 chlorine atoms. And therefore, the van der Waals forces are going to be weaker. Hence, the lower melting point. I would like to say this. This is an addition, okay? We're done with the Roman 2. When it comes to halogens, all halogens will have van der Waals forces, okay? But the van der Waals forces of, for example, chlorine are going to be weaker than those of iodine. And it's all tied to the size. Iodine atoms are larger because they have more energy levels. So iodine atoms are larger, therefore the molecules that they form will also be larger. Hence, stronger van der Waals forces. And that is the reason why you end up having iodine being a solid at room temperature. Okay. When it comes to chlorine or fluorine, they have smaller atoms and therefore they will form smaller molecules. Therefore, weaker van der Waals forces. Okay, I hope that is well understood and let us proceed to part C. Complete table 2 by giving the formula of the oxides of the elements and their acid-base character. Acid-base character simply means, are they acidic? Are they neutral? Are they basic? Evo 2. So let us just, Magnesium forms magnesium oxide, it's basic. Now, a lot of the metallic oxides tend to be basic, okay? Basic simply means that they form alkaline solutions or basic solutions. So, for example, if you were to take magnesium oxide, okay, add it to water, it's going to form magnesium hydroxide, which is a basic solution. Now, there are a few exceptions, like, for example, aluminium oxide. Yes, this is a metallic oxide, but it's not basic. It's amphoteric. Amphoteric meaning that it has both basic and acidic properties. And as such, it can react with both bases and acids. Tunazita ZAP, sio. Zinc oxide, lead oxide, and aluminium oxide. These are amphoteric oxides. Silicon 4 oxide, this is an acidic oxide. A lot of the oxides of non-metals tend to be acidic. Emphasis on a lot, not all. Okay? So, for example, silicon 4 oxide, phosphorus 3 oxide, phosphorus 5 oxide, these are all acidic bases. But sometimes you can have a non-metal reacting with oxygen, okay, to form an oxide that is not acidic. Case in point, water. Water is an oxide of hydrogen, but it's neutral. How about carbon 2 oxide? Carbon 2 oxide is an oxide of carbon, but it's neutral. Okay. Moving on to part D. Sulfur forms the chloride S2Cl2. Okay. Name, oh, by the way, this is known as disulfur dichloride. Just the way it is. Simnona sulfur nimbili, disulfur. Chlorine nimbili, dichloride. Okay, name the type of bond in the chloride. It's a covalent bond. When nonmetals bond with other nonmetals, in most cases, the bond, they use covalent bonds. Simnaona, okay? Yeah, the bond that is there. We use those horizontal lines to illustrate a covalent bond. Aye. Roman number 2, determine the oxidation number of sulfur in the chloride. Now, I don't know, at this point of the video posting, I don't know whether you have tackled electrochemistry in your respective schools. Okay, so I'm going to take it a bit slow so that by the end of it, you have understood, you should have understood this, even though you might not have tackled it in your schools. Okay, so we are supposed to determine the oxidation number of sulfur in the chloride. Now, oxidation number simply refers to the number of atoms that are either lost or gained by a species during a chemical reaction. Now, if you look at our compound, it's S2Cl2. We have 2 sulfur atoms and 2 chlorine atoms. Now, when you have a molecule as such or a compound, the overall oxidation number is going to be 0. Why am I saying it's 0? Are you seeing any charge attached to the compound? No. So if there's no charge, nikisema charge yani a positive or negative charge. If there's no charge, that means that it's neutral, and therefore the overall oxidation number is going to be 0. Now, what we're going to do is we are going to find out the specific oxidation number of sulfur. Remember, when you talk about oxidation numbers, they have to have a charge, either a positive or negative, to show us whether this particular species, chemical species, has either gained or lost electrons. So in this case, sulfur or chlorine will gain or lose electrons, but the number of electrons lost or gained will be in such a way that they will cancel each other, so that overall we have a neutral charge. Ndio maana hatuna any charge associated with the compound. Okay, let us start. I'm sure it will be clearer as we go. Sasa tumesema the oxidation number overall is 0. Now, when it comes to chlorine can have multiple oxidation numbers. Okay, it can have -1, it can have -2, quite a couple, but the most common one is -1. Okay, so -1 simply means that in a chemical reaction, chlorine will gain 1 electron, so -1. Now, how many chlorine atoms do we have? We have 2. So -1 multiplied by 2. So a total of -2 for the 2 chlorine atoms. So for sulfur, this is what we want to find out. As of now, we don't know the oxidation number of sulfur. So what we're going to do is we're simply going to assign it as S, and then tunaeka hapo 2 mbele, because we have 2 sulfur atoms. And then plus the negative charge, the oxidation number of chlorine, which is -2, equals 0. And from this point onwards, it's just easy. You are going to make the 2 sulfur atoms the subject of your formula on one side. So you're going to take the numerical value to the other side. And by doing so, it's going to change its sign from negative to positive. So 2 sulfur atoms is equals to +2. 1 will have a charge of +1. Mumeona hiyo? So 1 sulfur atom will have a charge of +1. And how many are they? We have 2. So a total charge of +2. Chlorine has a negative charge of 1 as its oxidation number. How many do we have? We have 2. So we have +2, -2, they cancel each other, and the charge of the compound itself is just neutral. Okay, if you need more time, you can, I've already stated this and I'm just repeating myself. Okay, tuendelee. Silicon tetrachloride fumes in air. Write an equation for the reaction. So there we have it. So silicon tetrachloride, okay. Just a minute. Okay. So silicon tetrachloride fumes in air because it reacts with moisture, with water that is present in the atmosphere. And it leads to the formation of silicon 4 oxide. This is just going to be a white powder, and hydrogen chloride gas. Now, Hydrogen chloride gas by itself is an invisible gas. It has a choking smell, yes, but it's an invisible gas. So if it's produced, you shouldn't see any fumes. By the way, it's not fumes like, I don't know what fumes, you know. So hydrogen chloride gas will not produce fumes. What produces fumes is that the hydrogen chloride will react with moisture present in the atmosphere to form hydrochloric acid. And the tiny drops of hydrochloric acid are what you see as fumes. Okay. Tuendelee. Oh, did I skip? Okay. I skipped, didn't I? Anyways, haya, tuendelee. So we are being told that silicon is a metalloid. Roman 1 state what is meant by the term metalloid. Now, this is an element that exhibits both metallic and non-metallic properties. Okay, let's discuss this a bit. Now, silicon is classified as a metalloid because its physical and chemical properties fall between those of metals and non-metals. You know, it has properties similar to metals, and again, it also has properties that are similar to those of non-metals. So, it's just called a metalloid. Iko hapo katikati. Now, physically, it's going to have shiny appearance that is typical of metals. But instead of it being malleable or ductile, as is the case for metals, it's brittle. Mara moja kuvunjika. Now, chemically, however, it reacts in a manner that is similar to non-metals. Okay? Yeah. So, ndo maana tunaiita just a metalloid. Now, I want to talk about one characteristic of silicon that is, let's say, very defining. Okay, and this is why it's where most of its uses comes in, and that is the conductivity of silicon. Now, silicon has electrical conductivity. No, it's not as good of a conductor as metals are, but it does actually conduct electricity to a degree, and therefore it's known as a semiconductor. So this simply means that, yes, conductivity is not as good as metals, but under certain conditions. For example, like when the temperature is increased, it can do so well enough. Hi. Okay. Stage 1 use of silicon as a metalloid. It's used as a semiconductor. Tumesema the reason why. And it's also used as, to make electronic components like TVs, tablets, phones, etc. Okay, on to question number 2. Part A. State the names of the following compounds. Okay, we have 2 compounds that have been given. And if you look at, the components, you can clearly tell that these are hydrocarbons, right? Because we only have carbon and hydrogen atoms that are present. So for us, okay, to be able to name these compounds, what we're going to do is, the first thing, we are going to count the number of carbon and hydrogen atoms that are present, okay? So that we can get a clearer picture. Now, from the molecular formula that we end up having, we will be able to tell whether these are alkanes, alkenes, or alkynes. And how are we going to do so? By looking at the general formulas for each of these 3. So each of these 3 has a general formula. So if we look at the number of carbon atoms that are present, we can be able to tell, okay, how many hydrogen atoms should be present if this was an alkane, alkene, or alkyne. Okay, let's just go into it. If we look at Roman number 1, we end up having a total of 7 carbon atoms and 16 hydrogen atoms. Okay, that is clearly an alkane because the general formula for alkanes is CnH2n plus 2. So if our n in this case is 7, 7 multiplied by 2 gives us 14, plus 2 gives us 16. This is clearly an alkane. Now, which particular one? 7 carbon atoms, that gives us heptane. Now, if we look at Roman number 2, do the same. What we will notice is that we have 6 carbon atoms. How many hydrogen atoms do we have? We have 10. This is an alkyne, because the general formula for alkynes is CnH2n minus 2. Our n is 6. 6 multiplied by 2 gives us 12. Minus 2 gives us 10. So this is an alkyne. Now, The name for this is going to be hexane because we have 6 carbon atoms and a triple bond, right? So hexane. Okay, that was an easy one. Haya, tuendelee. Now, part B. Part B, we are being told figure 1 shows extraction of copper from copper pyrite, okay, and that is the formula for copper pyrite. Now, this is the main ore for copper, for extraction of copper. So what I'm going to do is this. Before we tackle the question, I am going to take you briefly, okay, through the process of extraction of copper. And then when we go through the questions themselves, you are going to note that it's so much easier when you have the information and the content behind it. Now, I would like to say this. If, for example, metals is not a chapter that you have yet learned in school, or maybe you have, but you need a refresher course, I have a whole playlist dedicated to metals. By the way, I don't know whether you are aware, but we have more than 50 playlists in Cyclic. More than 50. You can just take time, okay, go through the playlists. I have them according to the levels. So we have them under Form 1, Form 2, Form 3, Form 4. And then I also have them according to the respective chapters present in chemistry and biology. Okay. We also have several playlists dedicated to practicals only. So take your time, go through the content. I am sure, even if you're a dedicated fan of mine, and I do hope you are, there are some videos that you might have skipped or you might be unaware of. Okay, so coming back to metals, I have 6 videos, okay, on the 6 metals for extraction, okay, that are based in our syllabus. And not only that, I also have additional videos that tackle past KCSE questions on respective metals. Now, metals was highly tested last year, as you're going to see. This is one question on extraction of metals. We are going to come across another question. And let me tell you this, candidates, metals is one of the easier topics in Form 4 chemistry. The easiest, I believe, is radioactivity, which I'm sure you're going to agree with me. And metals comes a close second. Don't be intimidated, okay, by the flowcharts only. As long as you have the content in the palm of your hand, nothing should be difficult. And there's nothing stopping you from going through those videos. And yeah, now one thing, okay, those were one of my oldest videos, okay, they were one of the oldest videos that I posted on Cyclic. You can clearly tell, by the way, because of the quality, and I used to use a whiteboard. So be gentle with me, okay, and understand. I get a lot of comments. Students are like, the writing on the board is not, coming off clear. And yeah, I do understand. That is the reason why I chose to change it to this new format, so that at the end, students can make out everything on the screen. But yeah, the content is still good, okay? Cringy, but still good. Coming back to extraction of copper. Now, when we talk about copper pyrite, we say that this is the chief ore for copper. Now, the process begins with heating the ore, okay? We heat the ore. This is a process that is called roasting. So, roasting is essentially heating the ore, okay, under high temperatures and in a controlled supply of air. So, essentially, we are heating the ore, okay, in a place that has air, so oxygen, right? Okay. Now, the goal here is to, number 1, remove some of the sulfur. You can clearly tell that there is sulfur present within the ore. Simnona S2. So the goal is to remove some of the sulfur by having it react with oxygen in order to form sulfur 4 oxide. Sulfur 4 oxide is a gas, so it just escapes, okay? Of course, it's going to be collected at some point because it's a pollutant, but it clearly separates from the remaining solid components. Now, the second goal is to convert some of the iron sulfide present. You can tell again, there's iron sulfide, known as your FES. So, to convert some of the iron sulfide present into iron 2 oxide by having it react with oxygen. So, when iron 2 sulfide reacts with oxygen, you end up having iron 2 oxide. Now, you might be thinking, why do we want these two to form oxides? We have an ore. This ore does contain copper, but it also contains a variety of other components that we need to get rid of. Our goal is, at the end, we need to have a compound or a component that has majority copper with very few impurities. Okay, yeah. So during this stage, the copper 1 sulfide, okay, is going to be largely intact. Okay, it's not going to react with the air. It's going to be the way it is. We will handle it in the later stages. Now, once it's roasted, okay, that is what happens in chamber 1. Once it's roasted, what will happen is that you are going to have the copper 1 sulfide, okay? There it is, Cu2S. Munona you Cu2S. Okay, the 2 there is the oxidation number of sulfur. So if sulfur has no, what is that? Hey, Mr. Howard, what do we call that? Anyways, in this case, the copper has an oxidation number of 1. Copper can have an oxidation number of 1 or 2, but in this case, it has the oxidation number of 1. And that is the reason why we refer to it as copper 1 sulfide. Okay, so the copper 1 sulfide is going to proceed, together with the iron 2 oxide, is going to proceed to chamber 2. Now, in chamber 2, we are having substance B being added, okay? Now, in chamber 2, what is going to happen is we are going to have addition of silica. Silica is simply silicon 4 oxide, okay? It's an oxide of silicon. Now, silicon 4 oxide is an acidic oxide. So what will happen is that if it comes into contact with iron 2 oxide, these two are going to react together. Iron 2 oxide is a basic oxide. Silicon 4 oxide is an acidic oxide. So they will react with one another to form a compound known as slag. And that is what comes out. It's removed as a waste product, although there are certain uses for it. Okay. When it comes to the copper 1 sulfide, it does not react. So it then proceeds, okay, into the third chamber. Now, in the third chamber, what happens is that you are going to have a reaction that occurs in 2 steps, okay? So in chamber 3, we are going to have 2 different reactions, one followed by the other. Now, in the first reaction, you are going to have some of the copper 1 sulfide reacting with oxygen. Let's pause there. Simnaona, air is being passed into chamber 3. So you're going to have copper 1 sulfide reacting, okay, with oxygen in the air. Now, this will lead to the formation of copper 1 oxide. Now, key point here to note is that not all of the copper 1 sulfide reacts with air. Only some of it reacts with air to form copper 1 oxide, okay? So this is reaction number 1, okay? So reaction number 1 occurs in plenty of air to supply oxygen for reaction with some of the copper 1 sulfide in order to form copper 1 oxide. Now, once that happens, we are going to have the supply of air being reduced, okay? Actually, it will either be reduced or it will be cut off completely. Now, for the second reaction to take place, we don't need a lot of oxygen present. In fact, the less oxygen present, the better. So in the second reaction, what we will have is we are going to have the copper 1 sulfide. Remember, only some of it reacted with oxygen, okay? So we're going to have the remaining copper 1 sulfide reacting with the newly formed copper 1 oxide. Let's pause there. Some of the copper 1 sulfide reacted with oxygen in the first step to form copper 1 oxide. Now, in the second step, the remaining copper 1 sulfide will react with the copper 1 oxide that has just been formed, okay? Now, this is our second reaction, and this will lead to the formation of molten copper metal and sulfur 4 oxide. So, sulfur 4 oxide being a gas, diffuses upwards and separates from the copper. So the molten copper is then going to be poured out, and as it cools, what happens is that any remaining sulfur 4 oxide that is present within will usually seek to escape because it's a gas, right? Yeah, kumbuka, we are going to have molten copper and sulfur 4 oxide being produced. Now, sulfur 4 oxide will seek to escape, right? Yeah. Now, when the molten copper is cooling down and you have sulfur 4 oxide, okay, moving upwards, it usually passes across the molten copper, not the molten really, because right now it's cooling. It passes across the cooling copper, and when it does so, it leads to the formation of bubbles, okay? Yeah, this is the gas escaping. So it leaves the surface of the copper looking blistered, kama ina madonda madonda, as you can clearly see. This is just because of the sulfur 4 oxide that is escaping into the surrounding. Okay, now this is what is known as blister copper, okay, because of its appearance. Now this copper, the one that is here, it's impure, okay. It's not 100% copper. It does contain impurities. So roughly 97.5% of this is copper. The rest, which is going to be around 2.5%, is going to be impurities. Now, these impurities need to be removed, because if they are not removed, they will affect the conductivity, electrical conductivity of the copper. So how is it purified? By taking this through electrolysis, such that at the end you end up having pure copper metal. Okay, that was a breakdown. Now let us go through the questions, see if we can now answer them, okay? Yeah, based on our discussion. Now, question part A, identify gas C, okay? Locate where gas C is. Gas C is coming out of chamber 3. Tulisema which gas is produced in the last chamber? Sulfur 4 oxide, okay? Okay. Part B, write an equation for the reaction that takes place in chamber A. Now, in chamber A, we are going to have roasting of the ore. So our equation should reflect that. So we're going to have copper pyrite being roasted in the presence of oxygen to form copper 1 sulfide, iron 2 oxide, and lastly, sulfur 4 oxide. By the way, sulfur 4 oxide is produced at multiple, okay, at multiple points within the extraction process. Okay, part C, identify substance B. Okay, substance B is the one that is being passed into chamber C. Tulisema in chamber 2, what were we doing? We were reacting it with silica, also known as silicon 4 oxide. Okay, this is so as to lead to the formation of slag. Okay. Part D, give the formula for the main compound in the slag. Now, in the slag, we are going to have iron silicate, okay, as such. Iron silicate. By the way, it's very easy to remember the formula for iron silicate, because we are talking about iron 2 oxide reacting with silicon 4 oxide. So what essentially you're going to do is you're just going to combine everything that is there. So we are going to have one iron atom, Fe. Silicon was also just one, Si, okay? And then oxygen atoms were 3. Okay, we have 1 from iron 2 oxide. Iron 2 oxide is FeO, right? So 1 from iron 2 oxide. And then silicon 4 oxide is SiO2. So 2 coming from silicon 4 oxide. A total of 3. And there we have it. So give the formula. The question is asking for the formula and not the name. So mnaona, by the way, vile tunavyo-flow. Haya. Part E, write equations for the 2 reactions that take place in chamber 3. Do you remember this? We talked about 2 reactions happening in chamber 3. In the first reaction, we had copper 1 sulfide reacting with oxygen to form copper 1 oxide and sulfur 4 oxide, okay? Now, in the second reaction, we had the remaining copper 1 sulfide, not all of it reacted with oxygen. So the remaining copper 1 sulfide reacting with copper 1 oxide, the one that was formed to form copper and sulfur 4 oxide. Okay. Now, if you need time in order to practice writing the equations, which is a very, by the way, a very uploadable, is that even a correct term? If you need time to write down the equations to practice doing so, pause the video and take as much time as you need. Haya, tuendelee. Part F, describe, okay, the process that is used to purify the impure copper. Now, the blister copper that is formed contains a few impurities, as stated before, and we need to remove as many of these impurities as possible, okay, if not all. Why? Because they are going to interfere with the electrical conductivity of copper. Remember, copper is used quite a lot in wires, okay? So we need it to be an excellent conductor of electricity. So that means that we need to purify it. Now, this is done through the process of electrolysis. Okay, so let's go through it. Now, when we talk about electrolysis, in electrolysis, we are going to have the following, okay? Number one, we are going to have an electrolyte. An electrolyte is a substance which, when in molten, okay, or aqueous states, can conduct electricity. That is point number one. It can conduct electricity. And point number two is that after conduction of electricity, it undergoes chemical decomposition. That simply means that it breaks down, right? Now, in this case, our electrolyte is going to be copper sulfate solution, okay? As you can clearly tell, it's blue in color. Now, we are also going to have electrodes. Now, we have two electrodes, the anode and the cathode, okay? Now, at the anode, this is where oxidation takes place. Oxidation is the loss of electrons. Now, the anode is always the electrode where loss of electrons takes place. At the cathode is where gaining of electrons occurs, right? So reduction, which is gaining of electrons, occurs at the cathode. Now, as you can tell, this is a redox reaction, okay? You are going to have one chemical species losing electrons, and these electrons are going to be gained by another. And that is the reason why when we talk about redox reactions, we say that reduction and oxidation need to happen simultaneously, at the same time. Because if you're talking about a chemical species gaining electrons, where are those electrons coming from? From another chemical species that has lost them. Okay. Now, if, for example, you are a student who maybe finds it confusing to remember, okay, what process occurs at the anode or at the cathode, these are mnemonics to help you. An-ox. At the anode is oxidation. Red cut. Reduction is at the cathode. Okay. Now, what will happen is that you are going to have copper 2 sulfate being electrolyzed. So, at the anode, we are going to use the impure copper, okay? The one that we obtained from the extraction process. Now, I would like to say this. These are two different processes. We have process number one, extraction, okay? Extraction, we are talking about removal and separation of the metal from its ores. This is extraction. And then after extraction, some usually undergo purification, okay, in order to obtain pure metal. Now, purification in this case is happening through electrolysis. So our anode is going to be the impure copper that we obtained from the extraction process. Ile yetu ya blister, okay? Now, when it comes to this process, what will happen is that at the anode, tumesema, we are going to have loss of electrons. So the copper atoms that are present in the anode are going to lose electrons and move into the solution to form ions. Let's pause them. We have copper atoms. Copper atoms are going to be present in the anode. Remember, the anode is just simply a piece of metal, right? And all matter consists of atoms. So we're expecting that this anode, the piece of copper metal, the piece of impure copper metal, contains atoms. So these atoms are going to lose electrons. And when metals lose electrons, they form positively charged ions. These ions are going to be copper 2 ions, as you can see. So they're going to go into the solution. Now, the electrons that have been lost will then flow through the wires, known as wires, connecting the two electrodes. So the electrons that were just lost at the anode will flow through the wires and move all the way to the cathode. Now, at the cathode, what will happen is that you are going to have the copper ions in the solution gaining the electrons in order to form copper atoms. Okay, so these copper atoms are then going to be deposited on the surface of the cathode. So over time, what we are expecting to see is that the mass of the cathode increases. Okay, why does it increase? Because we are going to have copper being deposited on its surface. Where did this copper come from? It came from the reduction of copper to ions to form atoms. Nikisema atoms, by the way, it's just simply copper metal. So at the end, you will simply take the cathode, and that cathode is going to contain pure copper metal. Okay, part G. When left exposed for a long time in air, copper coins turn green. Explain this observation. Now, in the past, okay, they used to have coins made of copper. No longer, okay? So you might have seen this concept. Let me show it to you. Not in coins, but in jewelry. In jewelry, or if you have, what are those? What are those called? The utensils, like, you know, in the past, they had those equipments that were made from copper. You will notice that over time, they turn green, okay? Now, the reason is because copper will react with carbon dioxide and water. Both of these are components that are naturally present in the atmosphere. Now, when it does so, it forms copper to carbonate, which is green in color. A lot of the time, we tend to think that, you know, all salts of copper are blue in color, but not really. You do have some salts of copper that tend to be green. A very good example is copper carbonate. We also have copper chloride, which is another copper salt that is green in color. So the green color you're seeing is as a result of formation of copper carbonate. Okay, proceeding to our next question. Question number 3, part A. State what is meant by standard enthalpy of formation of a compound. Okay, let's do this. Now, when it comes to the enthalpy, okay, enthalpy refers to the heat change of a substance, right, when it undergoes a certain reaction. So, in this case, we are talking about the heat change that occurs. Heat change means either you are going to have heat being absorbed or heat being lost. When we talk about chemical reactions, they fall under 2 categories. They can either be exothermic or endothermic. Exothermic reactions are those that release heat energy to the surrounding. Endothermic reactions are those chemical reactions that absorb heat energy from the surrounding. So whatever the case, you are going to have a change in the heat content, either through loss of heat to the surrounding or absorption of heat from the surrounding. So enthalpy is the heat change, okay, that occurs when 1 mole of a substance is formed from its constituent elements at standard conditions. So when we specify that we want the definition of standard enthalpy of formation, those are 3 things. We have enthalpy, not just enthalpy, but standard enthalpy, and then the enthalpy is that of formation of a compound. Now, I have explained what enthalpy is, okay? This is the heat change that occurs when heat is either gained or lost. Now, enthalpy of formation is the heat change that occurs when a substance is formed, okay? And the substance has to be formed from its constituent elements. So if I'm talking about the enthalpy of formation of water, then water needs to be formed from hydrogen and oxygen. Duh, because can we expect nitrogen and oxygen to give us water? No. So it needs to be formed from its constituent elements, and those are hydrogen and oxygen. Now, if we specify that we are looking for the standard enthalpy of formation, then that means that this needs to be conducted under standard conditions. What are standard conditions? We need to have a temperature of 25 degrees Celsius. We need to have a pressure of 1 atmosphere, right? And if we're talking about solutions, we need to have 1 mole. So in this case, when we talk about the standard enthalpy of formation of, for example, water, we are talking about the heat change that occurs when 1 mole of water is formed from its constituent elements at standard conditions. Okay, that's just an example, right? Yeah. Okay. Part B. Table 3 gives enthalpy of formation of some compounds. Write the thermochemical equations for the formation of carbon 4 oxide and water. Now, when we talk about thermochemical equations, these are, number 1, chemical equations, okay? Fully balanced chemical equations with the correct state symbols, right? And at the end, we are going to have the enthalpy, okay, denoted. So by enthalpy, I mean either the heat, the total heat evolved, or the total heat absorbed. So if we look at the first one, we are having carbon reacting with oxygen to form carbon 4 oxide, right? What is the enthalpy for this? It's negative 393 kilojoules per mole. What does that tell us? It tells us that when 1 mole of carbon 4 oxide is formed, 393 kilojoules of heat energy are released. And yes, it's released because by the negative sign, we can tell that this is an exothermic reaction. Exothermic reactions are denoted with a negative sign, okay? So both of these, formation of carbon 4 oxide and formation of water, are exothermic reactions that lead to the production of heat energy. And these are thermochemical equations. Okay, guys, let us proceed to the next question. Roman number 2, study the energy level diagram in figure 2 and answer the questions using the data in table 3. Okay, so we have an energy level diagram, as you can clearly see. Now we're being told to give the value of delta H1. Okay, let's break it down. We are going to start from the very top of the energy level diagram. Do you see where we have carbon reacting with hydrogen gas? That is where we're going to start. Now, that is our starting point, right? We are starting at that point, reacting carbon with hydrogen. Now, our end point, okay, is at the very top, at the very bottom. Uko chini, munaona? Where we have the end products being carbon 4 oxide and water. I just want to make this clear for us. Our starting point is at the top, where carbon is reacting with hydrogen gas. Our end point is at the bottom, where we have the products being carbon 4 oxide and water. Now, I want you to look closer. What you're going to note is that for us to move from the starting point to the end point, there are actually 2 routes we can take, right? We can take either of these 2 routes and we will start at the same point and end at the same point, right? So if we are to take the route on the left, okay, where there's delta H2, what you're going to note is that we will react carbon with hydrogen, and in just one step, we end up having carbon 4 oxide and water, and we are done, okay? Just that, straight to the point. We start with the reactants and end with the products in just a single step. Okay, now if we were to take the route on our right, okay, on this side, on our right, what you'll notice is that it's actually broken down into 2 steps. So we have step 1, which has the enthalpy of delta H1. And then we have step 2, which has the delta enthalpy of H3. So essentially, in this case, we start with the same reactants, and those are carbon and hydrogen gas. We end up at the same point with the same products being carbon 4 oxide and water. But instead of taking 1 step, we actually take 2 steps. But the starting point, the end point is still the same. Now, there was a guy called Hess. Hess came up with a law whereby he essentially states that it does not matter how many steps you take, okay? You can take 1 step, you can take 100 steps. As long as the starting point, okay, or the reactants are the same, as long as the products, okay, will be the same at the end, the energy content or the enthalpy is still going to be the same. According to Hess, the route does not matter. What matters is what the reactants were and what the products will be. So if the reactants and the products will be the same, such as in our case, then it doesn't matter whether you take a single step or 2 steps. As long as umeisha pahali pamoja, yeah, then the total energy will be the same. So what is my point? Nimeenda mbali, nimeenda kueleza mambo mengine hata I didn't answer. But it's okay. Let us just proceed since I've already dug up this hole for myself. So what Hess was saying is that the enthalpy for the single step, amboni delta H2, will be equal to delta H1 and delta H3 combined. Ya huku na za huku zitakuwa equal because we have the same reactants and we have the same products. Okay, I will come back to that, right? I will come back to that. And because there's a question ahead that asks this, so let us tackle that when we get there. Roman number 1, give the value of delta H1. Okay, now enthalpy, this enthalpy is that for the reaction between carbon and hydrogen leading to the formation of propane. Okay, C3H8 is propane. Now, this is the enthalpy of formation. Remember the enthalpy of formation? The standard enthalpy of formation, actually. So this is whereby you are forming 1 mole of a substance, in this case, that is propane, from its constituent elements. And these are carbon and hydrogen. So essentially, delta H1 is just the enthalpy of formation, standard enthalpy of formation of propane. And this is already there, by the way. It's already been provided in the table. Now, I don't know whether you've had a chance to look at the marking scheme for this particular paper. But if you have done so, what you're going to note is that this particular question has been cancelled out. And I believe the reason is because the answer was already there. It was just a matter of plucking it out from the table and then transferring the information into the answer part. Yeah. So anyways, we are looking for the enthalpy of formation of propane, and that is negative 104 kilojoules per mole. Right, eh? Okay. Let's proceed to the next part. We are told to calculate the values of delta H2. Okay. If we look at delta H2, this is the enthalpy change when carbon reacts with hydrogen. Okay. And we end up having carbon 4 oxide and water. Let's pause there. If carbon was to directly react with hydrogen, we would not get carbon 4 oxide and water. Because as we can tell from these two, these are oxides, okay? We have carbon 4 oxide and water. So for us to get these oxides, that means we had carbon reacting separately with oxygen, hydrogen reacting separately with oxygen, such that at the end, we end up having carbon 4 oxide and water. So when we talk about delta H2, we are talking about a combination of these two, okay? The enthalpy change when carbon, 3 moles of carbon, let me specify that, right? It's not just 1 mole, it's 3. When 3 moles of carbon react with oxygen to give us 3 moles of carbon 4 oxide. So before carbon 4 oxide, we have 3. So 3 moles of carbon gave us 3 moles of carbon 4 oxide on reaction with oxygen. Okay, and we are also looking for the enthalpy change whereby 4 moles of hydrogen reacted with oxygen to give us 4 moles of water, right? So these two combined will give us what we are terming as delta H2. So let's look at the first one, that of carbon. When it comes to formation of carbon 4 oxide, okay, hapo kwa table yetu, we are given the standard enthalpies of formation. That of carbon 4 oxide is negative 393. This is, okay, the heat energy that is released when 1 mole of carbon 4 oxide is formed. How many moles are we forming at this point? 3. So whatever we have, negative 393, we will multiply it by 3. Because 3 moles of carbon 4 oxide are being formed. And we end up having negative 1179 kilojoules. Okay, haya. Tunaendelea huku kwa upande wa pili when it comes to water. Now, if you look at water, the standard enthalpy of formation is negative 286. So this is the heat energy that is released when 1 mole of water is formed. How many moles of water are we forming at this point? 4. So negative 286 multiplied by 4 will give us negative 1144 kilojoules. And we are going to sum these two, and we end up getting negative 2323 kilojoules. So this is going to be our delta H2. Okay, guys? Just a minute. Hiya. Now, let us proceed to the next part. Now, in the next part, we are being asked to calculate the values for delta H3. Okay? Delta H3 ni gani? Ni hapo. Now, this is the heat energy. Okay? This is the heat change when you have 1 mole of propane. Okay? Undergoing a process leading to the formation of carbon 4 oxide and water. Just look at it. We are starting with propane, hapo katikati, and then we are ending up with carbon 4 oxide and water. Now, propane is a hydrocarbon. When you burn it in air, okay, it's going to react with oxygen to give you carbon 4 oxide and water. So essentially what we have is the enthalpy of combustion of propane. We are combusting propane, okay, reacting it with oxygen to form carbon 4 oxide and water. Now, remember what we talked about before, Hess's law? Hess's law says that it does not matter, okay, whether it occurs in a single step or in 2 steps or in more steps. As long as the reactants and the products are the same, then the total energy content for both will be equal. So that means that delta H2, okay, it will be equal to delta H1 plus delta H3, as you can see from the mathematical expression. So if we were to take delta H1, add it to delta H3, it will be equal, the value we get will be equal to delta H2. So if that is the case, and we already know what delta H2 is, we already know what delta H1 is, isn't this easy for us to get delta H3? Yes, it is. So delta H3 will simply be given by taking delta H2 minus delta H1. So if you go through that, and you will end up having the following value. And just a point of note, the signs are very important, okay? The negative sign is very important because it illustrates what type of a reaction this is. So this is an exothermic reaction and you need to illustrate it as such. And by the way, the end answer for delta H3 has to have a negative sign. Why? Because when we talk about enthalpy of combustion, it's always exothermic, okay? When you burn something in oxygen, it will always release heat energy. So that means enthalpy of combustion will always have a negative sign. And I believe this is one of the few enthalpies that always is a particular one. When we talk about the other enthalpies, they can either be exothermic or endothermic, right? But when it comes to combustion, the enthalpy of combustion, it's always negative because heat energy is always evolved when you burn something in oxygen. Okay, a deep breath for me before we proceed. By the way, guys, I would like to say this. I appreciate the positive comments that some of you include in the videos. Okay, they mean a lot to me. And I would like to say this. A lot of individuals tend to have the misconception that YouTube pays its creators. Is that the right time? YouTube pays its creators well. And yes, this might actually be true, but unfortunately, it's not really true for the teachers in Kenya. When it comes to YouTube payments, it's usually based on the advertisers. Okay, we have very few advertisers here, and they are not willing to pay as much. So at the end, whatever trickles down to us, the fraction we get from YouTube is very, very little. So I would like to say this. As teachers, majority of us do this for the love, for the passion of teaching, okay? And also in order to extend assistance to students. So when we get these comments, they usually motivate us, okay? I'm speaking on behalf of the others, but personally, I love the positive comments that students share with me. Sometimes I will be in a slump, okay? And I'll be like, I don't feel like creating a video. And then I'm sitting there and I happen across, I open the YouTube studio and I happen across a comment from Carol, a comment from Aisha, a comment from Kip, and it makes my day. And I'm like rejuvenated. I'm like, it's been so long since I've created a video. Let me do so today. So just for those that do share comments, thank you for that. For those that give it a thumbs up, and also, what else can you do? Okay, maybe share with your friends, your mates. I really appreciate it. By the way, doing so usually sends a signal to YouTube that this video is good. So they tend to recommend it to so many more students. And by the way, that is the goal of this channel, right? We want students to benefit from this channel. The other day, I saw a comment from a student. He's a candidate, and he was like, I haven't been aware of your channel. He's a candidate, so amekuwa akitumia YouTube for long, but this is the first time he's hearing of my channel. So his wish was that he knew of it, sooner. So my point is this: there's so many students in Kenya that are unaware of Cyclic. If you can manage to share, okay, or like, yeah, it's sending a message to YouTube, and hopefully they will be able to show it to others. Okay, enough. Let us proceed. Roman number 3. When a sample of butane was burned, the heat produced raised the temperature of 500 grams of water by 35 degrees Celsius. Okay, let's stop there. We are talking about burning butane. Tumesema nini sasa hivi kuhusu burning a substance? When you burn a substance, heat energy is always evolved. Okay, so that means this is an exothermic reaction. And by the way, this was the first hint. The second hint is the temperature was raised by 35 degrees Celsius. Okay, so we had an increase in temperature because heat energy was evolved. So exothermic reaction. Now, just a point of note, the temperature was raised by, so that means this is the change in temperature. You've already been provided the change in temperature, and that is 35 degrees Celsius, which would be equal to 35 Kelvin. So the specific heat capacity of water is 4.2 joules per grams per Kelvin. Calculate the heat change for the reaction. Okay. Higher. Now, for us to calculate the heat change, we are going to use the following formula. Mass, okay. The M refers to the mass of water, which in this case is 500 grams, right? Multiplied by the specific heat capacity, which is 4.2, multiplied by the change in temperature, which is 35. So we end up having 73,500 joules. Okay. Now, at this point, some students usually convert it to kilojoules, and that is also okay. Okay. So if you want to convert it to kilojoules, you can simply divide the answer by 1000, which will give you 73.5 kilojoules. Now, I would like to draw your attention to the kilojoules, okay, to the sign. The J for the joules is supposed to be a capital letter, but the K is supposed to be a small letter. Now, how do we know that this is a small letter? Look at the way the K is written. I don't know what it's called, but unaona hiyo mstari ulosoma juu and then ako ka nyingine kimeshuka chini. That is a small letter. Now, that is very different from how a capital letter is written. Look at where specific heat capacity of water is. Mumeiona hiyo specific heat capacity of water? 4.2 joules. per gram, per Kelvin. That is how a capital K is written. Look at the difference between the K for the capital letter and that of the small letter. So ukiandika kilo ni a small letter. Okay. Now, if you need more time, pause the video, okay? So we are being told Roman number 2, the mass of butane that was burnt, given that the heat of combustion of 1 mole of butane is negative 2880 kilojoules per mole. Okay, let's pause there. We are looking for the mass of butane that was burnt. Okay, we don't know what it is, but we need to determine it based on the information that we have been provided. Now, the sample that we used of butane evolved 73,500 joules of heat energy, the sample that we used. But we don't know the specific mass of the sample. That is what we want to find out. Now, in Roman 2, we are provided with an additional tip, okay? And that is, if you were to take 1 mole of butane, burn it in oxygen, you will evolve 2880 joules of heat energy. Actually, not joules, kilojoules of heat energy. Let me repeat that. If you were to take 1 mole of butane, it will evolve 2880 kilojoules of heat energy. Kilojoules of heat energy. Now, I would like to say this at this point. The answer that we got in Roman 1 is in joules. So for us to proceed, you need to have these two having the same units. You can decide whether they have the same unit as in joules or kilojoules. Either will get you towards the right answer. But you cannot use one in joules and the other in kilojoules. You will end up having the wrong answer. So let us use that in kilojoules, okay? So tumesema 73,500 divide in kilojoules will give us 73.5. Haya tuanze. Now, if 1 mole of butane evolves 2880 kilojoules, what about ile yetu? Ile yetu ili evolve ngapi? 73.5. How many moles were present in that sample? So you cross multiply and you get 0.0255 moles. Let's pause there. In the sample that we had, it evolved 73.5 kilojoules of heat energy. We don't know how many moles were there, what was the mass. That is what we intend to find out. Now, what is going to be our starting point? We were told the molar enthalpy of combustion of butane. If you take 1 mole of butane, burn it, it gives you 2880 kilojoules. What about ours, the one that evolved 73.5 kilojoules? How many moles will be present? And there is our answer. Now, we know the moles that are present right now in the sample that we had. So this last step is simply just getting the mass. And this is very easy. If we want the mass, we need to take the number of moles multiplied by the RMM of butane. The number of moles is 0.0255. What is the RMM of butane? This is something we can easily get. Molecular formula of butane is C4H10. Carbon has an RM of 12. How many are they? There are 4. 12 multiplied by 4 gives you 48. Hydrogen has the RM of 1 multiplied by 10 added to 48 and unapata ngapi? 58. So the relative molecular mass of butane is 58. We know the moles, we know the RMM. If we multiply these two values, we end up having the mass. And the mass of butane that was present in the sample that was burnt was 1.48 grams. And there we have it. Okay, let us proceed to our next question. Number 4, figure 3 is a flowchart showing some reactions of chlorine, okay? So we are going to start with where chlorine gas is, hapo katikati. So let's move towards the right. Chlorine gas will react with iron to form compound C. Okay, so compound C is going to be iron 3 chloride. Okay, chlorine gas will undergo step number 2 to form sodium chlorate. Okay, and then chlorine gas will undergo step number 3 where it reacts with phosphorus to form compounds D and E. So chlorine reacts with phosphorus to form phosphorus chloride. But to be specific, it will form phosphorus 3 chloride or phosphorus 5 chloride, right? So compounds D and E are these two chlorides. Okay, let us start. Give the name of compound C formed in step number 1, that is iron 3 chloride. Roman 2, state the reagent and the conditions necessary for the reaction in step 2. So the reagent in step 2 is sodium hydroxide solution. So if we react chlorine gas with sodium hydroxide solution, we end up having the following compound. Now, what are the conditions? The conditions are the sodium hydroxide solution needs to be, number 1, it needs to be hot, okay? And number 2 is that it needs to be concentrated. Where am I? Yeah. Roman number 3, 2 compounds are formed in the reaction in step 3. Give the formulae of each of the 2 compounds. So as stated before, D and E are the 2 chlorides. Now because they haven't specified, if you write D as phosphorus 3 chloride or phosphorus 5 chloride, it's okay. E ukija ukiandika any of those 2, it's also correct. As long as you don't repeat yourself, then yes, it's okay. And remember, the question is asking you for the formulae, okay? It's not asking for the names, but the formula. Part D, state the observation made when Roman 1, chlorine gas is bubbled into aqueous potassium iodide, okay? So our observation is that a brown solution will be formed. Now, when chlorine gas is bubbled, it's passed through potassium iodide. Potassium iodide, by the way, is colorless, right? I believe all of the compounds of potassium, is it all or most? Okay, tend to be colorless, right? So potassium iodide solution is going to be colorless. Now, when chlorine gas is bubbled through the colorless solution of potassium iodide, we are going to have a displacement reaction, right? Because in potassium iodide, we have iodide ions, and chlorine is more reactive than iodine. So chlorine is going to oxidize the iodide ions to form iodine, which is brown in color. Essentially, it's going to displace, okay, the iodide ions. So the iodine are going to form the brown solution. Roman number 2, moist red litmus paper is placed in a gas jar of chlorine gas. Okay. Now, the observation is that the moist red litmus paper is going to be bleached white. It will turn white. Now, this occurs because chlorine reacts with the moisture on the litmus paper. Okay, so it dissolves in the moisture to form a mixture of 2 acids. We have hydrochloric acid and chloric 1 acid. Now, hydrochloric acid is not involved in the bleaching process. Okay, it's a stable acid. It's going to remain the way it is. Chloric 1 acid is the one that is responsible for the bleaching. So what happens is that chloric 1 acid is going to break down to form hydrochloric acid and an atom of oxygen. This atom of oxygen is what we call nascent oxygen. It's very active. So it's going to combine with the dye, causing it to become colorless. And that is why it's bleached white. Part E, write an ionic equation for the reaction that takes place when aqueous lead 2 nitrate is added to aqueous potassium chloride. Okay, that's quite a lot. So essentially, we are having a reaction between lead to nitrate. This is a colorless solution. It's soluble, reacting with potassium iodide. Again, potassium iodide is also colorless. So we are having two colorless solutions reacting with one another. Now, what will happen is that you are going to have a double displacement reaction. Essentially, they're just going to be swapping, okay, swapping the ions. So we're going to end up having lead 2 iodide being formed and potassium nitrate being formed. Potassium nitrate is colorless. Lead 2 iodide, this is yellow in color and it's a precipitate because it's insoluble. The manner the state symbol is S. So it's insoluble and it forms a precipitate and it's yellow in color. So our ionic equation is the one that is in blue, right? Now the potassium ions and the nitrate ions are just spectator ions. Ziko tu hapo, zina peleka wengine, they are not literally participating in the reaction. Part F, state the reason why chlorine is used in water treatment. It kills the pathogens in the water. Okay, guys, let us proceed with question number 5. Okay, so part A, figure 5 shows the Downs cell used in the extraction of sodium from molten sodium chloride. Okay, now this was the reason why I stated that the metals, the chapter of metals is very crucial to understand, okay, for the candidates. Because in last year's paper, just imagine in paper 2, it was tested twice. First in the extraction of copper and now in, the extraction of sodium. Okay. Haya, sasa tuanze, tueleze Downs cell ni nini. Okay, actually, what I'm going to do is I am going to explain, of course, because I want you to understand by the end of this paper. But if you need further details, okay, or if you need to understand in depth, I highly recommend you check out extraction of sodium, by the way. Yeah, it's going to help you quite a lot. Now, when we talk about Roman 1, identify the anode and the cathode in the cell and give a reason. Now, when we talk about extraction of sodium, extraction of metals that are more reactive, what happens is that the extraction process is usually on electrolysis, okay? Metals like aluminium and sodium are usually extracted through this process. Now, I know we just talked about electrolysis in copper, but that was not in the extraction process. It was actually in the purification process. Now, in these metals, like in sodium, they are extracted from their ores through electrolysis. Now, the main ore that is used in extraction of sodium is rock salt, okay? And this is essentially just sodium chloride. So the anodes and the cathodes, remember we have to have these two in electrolysis. So the anode, okay, the anode is going to be B, okay? Just take a look at where B is. And remember, B, on upon make a plus sign, yes, because in electrolysis, the anode is the electrode that is connected to the positive terminal. So reason being that the chloride ions are going to be discharged at the positive electrode. Now when it comes to electrolysis, what happens is that you are going to have the ions migrating, right? So you're going to have two sets of ions, the ones that are positively charged and the ones that are negatively charged. So the negatively charged ions, in this case, we are going to have the chloride ions, are going to be attracted to the positive electrode, which is our anode. So that means they are going to be discharged at this point. So unaona hapo chlorine gas, it's immediately released just above where the anode is. Okay, now the next part, we are supposed to identify where the cathode is. Okay, so at this point, it's just going to be electrode A, right? Now in electrode A, this is going to be the negatively charged electrode. So sodium ions are positively charged. So they are going to be attracted towards the negative electrode, where they will then be discharged. Nixima discharged, this is whereby you are going to have either reduction or oxidation taking place. Roman number 3, set the purpose of the steel gauze diaphragm. Okay, let's first locate where the steel gauze diaphragm. Now, if you look at the diaphragm, it's literally just surrounding, the anode. So now it's surrounding the anode. Now, by doing so, it's separating the anode from the cathode. Now, at the anode, we are going to have production of chlorine gas. At the cathode, we are going to have production of sodium metal. Now, both sodium and chlorine are very reactive. So, if they were to come into contact with one another, what will happen is that they will react with one another to give us back sodium chloride, what we started out with. So, essentially, we're just going to be at square one. Do we want this? No. Because this is for the extraction of sodium. Our final product has to be sodium. So we need these two separated so that we can end up collecting sodium separately and chlorine gas. Of course, chlorine gas is not going to be allowed to escape, right? It's usually scrubbed to prevent its release into the surroundings since it's a pollutant. So the function of the diaphragm. So essentially the diaphragm is just a structure that is made of steel that separates the anode and the cathode. Okay, it prevents sodium and chlorine from recombining. Okay, we talk about recombining because they were combined initially in sodium chloride and then separated. So if they were to do so once again, it will just be recombining. Part B, table 4 shows the melting and boiling points of sodium and sodium chloride. So of sodium metal and sodium chloride. Okay, so let's go through the table. So when it comes to sodium, the melting point is 97.8, quite low actually, right? The boiling point is 890. So essentially these are the temperature points whereby sodium metal, in solid state melts to give you a liquid. That is the melting point. The boiling point where it forms vapor. Sodium chloride has a higher melting point at 801 and a much higher boiling point at 1467 degrees Celsius. Now, Roman 1, given that the Downs cell is the structure that you just saw. Now, given that the Downs cell is operated at 600 degrees Celsius, state how this temperature is achieved. Okay. Now, when we talk about in the Downs cell, okay, so we are going to have addition of calcium chloride. Calcium chloride is going to lower the melting point of sodium chloride. Let's pause there, okay? We need sodium chloride to be in molten state, right? Yeah, we need it to be in molten state. Sodium chloride is an ionic compound. That means it can conduct electricity, but only if it's in aqueous state, in solution form, or if it's in molten state. Now, in the Downs cell, sodium chloride tends to be in molten state. It's heated until it liquefies so that it can then conduct electricity, and we can have decomposition leading to the formation of sodium metal and chlorine gas. Now, the melting point of sodium chloride is 801. This is what we started out with, right? It's our O, 801. But tumeambiwa the temperatures in a Downs cell are operated at around 600. 600 is lower than the melting point of sodium chloride, which is 801. So kama tuna 600 temperatures, okay? And the melting point of sodium chloride is 801. How do we ensure that it melts at the lower temperature? Let's pause there. Sodium chloride normally will only melt at temperatures above 800 degrees Celsius. But in the Downs cell, it melts at temperatures that are at around 600 degrees Celsius. How is this possible? Now, through the addition of an impurity. Impurities lower the melting point. When you talk about impurity, it's simply a substance that does, It does not belong. Okay. So in this case, we are going to add an impurity in the form of calcium chloride. It's going to lower the melting point of sodium chloride from around 801 to around 600, therefore allowing it to melt at the lower temperatures. Okay. Now, you might be thinking, okay, why do we need to do this? Why do we need to add calcium chloride in order to lower the melting point of sodium chloride? Money. Just imagine how much fuel will be needed, okay, to melt sodium chloride at temperatures above 800. If we were to lower this melting point to temperatures around 600, won't we be saving costs? Won't we be lowering the cost by saving on fuel? Yes, we would be. So it's economical because it lowers the cost. Roman number 3, state the physical state in which sodium is obtained from the cell. Give a reason. Now, the sodium metal, okay, at the end of electrolysis, we are going to end up having sodium metal. Sodium metal is going to be in liquid state. The temperatures are going to be around 600. What is the melting point of sodium? 97.8. So at 97.8, you will have sodium metal melting to give you a liquid, okay, liquid sodium, right? So if you have temperatures that are much higher, at around 600 degrees Celsius, we are expecting the sodium metal to be in liquid state. Part D. Explain how a sample of solid sodium should be stored in the lab. Now, sodium is highly reactive, right? It will react with carbon dioxide. It will react with water, with oxygen, okay, in the atmosphere. So in order to prevent any unnecessary events, what happens is that it's usually stored in liquid paraffin or oil. So this prevents it from reacting with oxygen, moisture, or carbon dioxide in the surrounding. State one industrial use of sodium. Now, there are so many industrial uses of sodium. Pick one correct one, write it down, and you earn yourself a mark. Proceeding to question number 6. The products of electrolysis depend on the conditions used. Part A, Roman 1. State the conditions if the products of electrolysis of aqueous copper 2 sulfate are Roman 1, oxygen and copper, Roman 2, copper. Okay. Now, let's break it down, okay? Now, if we have, okay, just a minute. Okay. Now, if, for example, we have electrolysis of copper 2 sulfate and we are using graphite electrodes. Now, graphite is a good conductor of electricity. It's essentially an allotrope of carbon, but because of the presence of delocalized electrons, it can conduct electricity. Now, one thing about graphite is that it's inert, okay? It does not participate in the chemical reactions. So, whatever products you end up forming are not because graphite participated in the reaction. No, it's because of the electrolyte. So if we were to use graphite electrodes, what will happen is at the anode, you will always have oxidation, the loss of electrons. So you are going to have oxidation happening, and the oxidation is, oh, I just realized something. Disregard the half equation for the hydroxide ions, okay? Yeah, disregard it. It's wrong. The electrons are supposed to be on the other side of the equation. Okay, so what I was saying is that when it comes to the anode, what will happen is that we are going to have hydroxide ions being discharged. When I talk about discharged, that means ions either undergo reduction or oxidation. So on discharge, we are going to end up having oxygen gas being released, okay? And that is what you see. Now at the cathode, you are going to have copper 2 ions being discharged, they will gain electrons and they will form copper atoms, which are going to be deposited on the cathode. Remember what we said, at the cathode, it's always reduction taking place. So, oxygen and copper are produced when graphite electrodes are used. Now, if we were to use copper electrodes, what would happen is that we are only going to get copper metal, okay? No oxygen gas will be produced. Now, at the anode, what will happen is that you are going to have copper atoms present, okay, in the copper electrodes, losing electrons and then going into the solution as copper ions. Okay, yeah. So no discharge of hydroxide ions. It's going to be the copper atoms that will be preferentially discharged. So they will lose electrons, go into the solution, air to form copper ions. Huku kwa cathode, copper ions in the solution will gain electrons and be deposited as copper atoms on the cathode. So essentially, you will just have copper, okay, being deposited on the cathode. No discharge of hydroxide ions and therefore no oxygen gas. Okay, Roman number 2. During electrolysis of an electrolyte containing aqueous, okay, A3 plus ions, 19.4 grams of A were obtained when a current of 15 amperes was passed through it for 2 hours. Roman number 1. Write the half equation for the reaction that took place. Just a minute. That is weird. Is this actually recording? Strange indeed. Okay, let's go with the assumption that it is recording, although I am not seeing it. Okay, so Roman 1, the half equation for the reaction that took place. So we are going to have the ions gaining electrons in order to form the atoms. Okay, and since the ions have a positive charge of 3, they are going to gain 3 electrons each to form the atom. Roman number 2, determine the relative atomic mass of A. Okay, so we are being told that 1 Faraday equals 96,500 coulombs. Acha tuanze. So we are going to use the half equation to guide us, right? So from the half equation, we know that 1 mole of A needs 3 moles of electrons in order to be deposited. Si tunaona? Yeah, we need 3 moles of electrons. Now, 1 Faraday is equal to 1 mole of electrons and it's equal to 96,500 coulombs. So that means for us to use the 3 moles of electrons, we need 3 Faradays. So 3 multiplied by 96,500 will give us 289,500 coulombs. That is what we need, okay, for the formation of 1 mole of A. We need 3 Faradays, that is equal to that. Okay. Now, in the next part of our question, right, we know, okay, so when we look at the information that we have, okay, we are being told that 19.4 grams of A was obtained when a current of 15 amperes was passed through it for 2 hours, right? So if we want to find, okay, the specific, what was it? Charge that was used to get 19.4 grams of A, what we are going to do is we are going to use the formula charge is given by IT. Sorry for that, I forgot to include it here, okay? So charge is given by IT, I being current, T being time in seconds. So our current is going to be 15. The time is going to be in seconds. So if we were to convert, okay, 2 hours into seconds, 2 hours, we will take 2 multiplied by 60 multiplied by 60, right? So at the end, we will get 108,000. Let me just check here. 108,000 columns. I'm sorry, I forgot to include this part. So 108,000 columns. So what is this? This is the charge, okay, that led to the formation of 19.4 grams of air. 19.4 grams of air were formed when a current of 15 was passed through 2 hours. So if we were to take 15 multiplied by the time in seconds, we will get 108,000 coulombs. So 19.4 was obtained when a current of 108,000 coulombs was passed through it. Sorry, not a current, when a charge of 108,000 was used. Now, what about if we used a charge of 289,500? You might be thinking 289 natokapi. Remember at the very beginning, tulisema based on our half equation, for us to get 1 mole of air, we need to use 3 moles of electron. And a mole of electron is equivalent to 1 Faraday, which is equivalent to 96,500. So 3 moles of electrons will have a charge of 289,500. So coming back to this, if what we used was 108,000 and it gave us 19.4 grams of air, what about if we want 1 mole, okay? And we know that for us to get 1 mole, we need to use 289,500. So you substitute this and you end up having 52, right? So 52 is going to be the mass of air, which is the RM of air. Okay, now I am going to give you, no, I'm not going to give you. You will take time, okay? Pause the video, go through it. Do the calculations by yourself and then, hit play and we can continue together once more. Part B, study the following cell representation diagram and answer the questions that follow. Okay, so we have nickel. So upon nickel S, that means the electrode that was used was nickel. Nickel is a metal. A solution of nickel ions was also present. And then we have the 2 vertical lines. Those represent the salt bridge. And then we have silver, a solution of silver ions, and then a silver electrode that was used. And then we're told that the standard electrode potential for this cell is plus 1.05 volts. So Roman 1, state what that symbol represents. This is the salt bridge. Roman number 2, write an equation for the reaction that occurs in the cell. Okay, so we are going to take it step by step, okay, and then arrive at the final answer together. Now, in the first instance, we are going to have atoms, okay, present in the nickel rod. Remember tumesema? By the way, when you see the cell representation, whatever is on the left is the anode. And at the anode tumesema, it's where oxidation takes place. And oxidation is the loss of electrons. So that means we are going to have atoms in the nickel rod, okay, losing electrons and going into the solution to form nickel ions. There we have our half question. Now, on the right side of the cell representation, that is where the cathode is. So the cathode is where we have the silver half cell. So if we look at the cathode is where reduction takes place, and that is the gaining of electrons. So we are going to have ions, okay? The ions of silver ions are going to gain electrons and then be deposited as silver metals on the electrode. Now, I would like to say this. In most of the cases, when it comes to the anode, okay, it's always atoms that lose electrons in most cases, okay? When it comes to metals, by the way, like in this case, we have metals, we have nickel and silver, right? So if you have such a setup, at the anode, it's going to be the metal atoms losing electrons to form ions. At the cathode, it's going to be the metal ions gaining electrons in order to form atoms. Now, if we were to combine these two half equations, we are going to get the following. Now, I want you to know this. Whatever is on the left side of the equation, that represents the reactants. So if you look at our half equation on nickel, nickel is on the left side of the equation. Left side, angalia mkono wako kulia, is on the left side of the equation. So the nickel, the one that is in solid state, represents a reactant. Tukija huku kwa upande wa the silver half cell, on the left side of the arrow, we have the silver ions. So those two are going to be on the reactant side of the equation. Nickel ions and silver atoms, those are on the right side, okay, in the half equation. So they will also be on the right side of the ionic equation. We don't include the electrons in this case. Okay, let us proceed. Now, there was an error with Roman number 3. I believe we had missing information. Okay. Did we have missing information? I remember there was an error. Let me just check and confirm because it's not in my slides. Yeah. So there was an error with Roman 3 and it was not marked in the KCSE paper. So we are going to ignore that to proceed to Roman 4. State how the EMF of a cell can be used to predict whether a reaction is feasible. So wakisema whether a reaction is feasible, yamaanisha can the reaction actually take place or not. Now let's go back to our equation. If you look at our equation, hapo juu, the standard electrode potential was plus 1.05, okay? So the positive sign over there. Now if you have a standard electrode potential, okay, of a cell, the EMF of a cell, and the EMF of a cell, okay, is positive, that means the reaction can occur by itself. If it's negative, then that means the reaction is not feasible and it cannot take place. So there we have it. Part C, corrosion of a metal involves formation of an oxide layer on the metal surface. Now, when we talk about corrosion, corrosion occurs when a metal reacts with oxygen, right? Now, when the metal is iron, we refer to it as rusting. But when the metal is any other, tunaita corrosion, okay? Now, it involves a metal reacting with oxygen to form an oxide layer on the surface. So explain why corrosion of aluminium is protective while that of iron is destructive, okay? Higher. So essentially they're asking, why would corrosion of aluminium be good while that of iron be bad? Now, when we talk about aluminium, aluminium reacts with oxygen to form aluminium oxide. Now, aluminium oxide is inert. It's unreactive, okay? And it's non-porous. It forms this uniform covering on the surface of the metal, okay? And it's inert. So what happens is that by forming this protective layer, it actually protects the metal beneath it and therefore prevents the metal from being corroded or reacting further with other elements. So essentially, it's good because it seals off the metal and protects it. Iron reacts with oxygen to form iron oxide. Just look at it. Now, iron oxide is porous. Simnaona hizo nafasi nafasi. Yeah. So oxygen, water can actually penetrate to get to the metal below it and cause further reaction. So inaingia huko ndani, metal ina react huko chini, inaendelea tu kureact, you know? And the rust flakes off easily. I think this is something you've seen. Ukishika tu kidogo ina flake, yeah? So when it flakes off, I don't know another word. When it flakes off, it exposes the metal to further corrosion. So essentially, it's not good. It's not protective in nature. It's actually even worse. Question number 7. Part A. State and explain how the rate of the reaction is affected by an increase in pressure, by an increase in temperature. Okay. Now, if we look at the reaction, it's A reacting with B to form AB. Now, when we talk about pressure, it's always about the volume, the number of molecules present, okay, the number of particles present. Now, if we look at the equation, we can break it down into two parts. where you have the reactants and where you have the products. Now we have 1 mole of A reacting with 1 mole of B to give us 1 mole of AB. So on the reactant side, how many moles do we have in total? 2. 1 mole of A and 1 mole of B. So a total of 2 moles. On the product side, we only have 1 mole. So we have 2:1. Now, if we were to increase the pressure, an increase in pressure will always favor the side that has a lower volume, right? Yeah. So, where am I? Yeah. So when we increase the pressure, it's going to increase the forward reaction where we get more of AB. Okay, so the reaction is going to increase. So A will react more with B in order to form AB. Why? Because AB has lower volume. Okay, remember Boyle's law, pressure and volume are inversely related. You increase the pressure, it's going to favor the side that has the lower volume, the lower number of particles. So by decreasing the volume, the particles are brought closer together, thus increasing the number of successful collisions. By the way, I also have several videos explaining how different factors affect the rates of reaction. So if you are in the mood for it, check it out. Now, Roman 2, temperature. When we talk about temperature, temperature increases the kinetic energy of particles. So it causes the particles to move faster. And if particles move faster, they are more likely to collide with one another. So increasing the temperature increases the kinetic energy of the particles. This increases the number of successful collisions. What are successful collisions? These are collisions that lead to the formation of products. Sometimes reactants, the particles of reactants collide with one another and then just bounce back without forming a product. These are called unsuccessful collisions. But if they, collide with one another, leading to the formation of a product, those are what we call successful collisions. And those are the ones that we want. Okay. Part B, the rate of reaction between ethanoic and copper 2 carbonate can be monitored by measuring the volume of the gas produced. The results obtained using 75 cubic centimeter of 0.1 molar ethanoic acid and excess copper 2 carbonate are shown in the table. Okay, so if we look at the table, we can tell that as time proceeds, okay, we start with the initial one and we end up to 80 seconds. As time proceeds, the rate of the reaction speeds up and then it slows down and stops. So as we can see on the 70th and 80th seconds, we have the same volume of gas collected. So that means the final volume of gas collected. So that means at this point, the reaction has stopped. Okay, write an equation for the reaction that took place. So we have copper carbonate reacting with ethanoic acid. When you have a carbonate reacting with an acid, you get a salt, water, and carbon 4 oxide. So we end up having copper ethanoate, and water and carbon 4 oxide. Okay, Roman number 2, give a reason why excess copper 2 carbonate was used, okay, to ensure that all the acid has been used up, right? So when the reaction finishes up, what will happen is that all the acid would have been used up, but because copper carbonate was used in excess, some of it will be left unreacted. Roman number 3, on the grid provided, draw a graph of the results obtained. Okay, so what I will do is, I am going to provide you with the graph. You can take the time, go through it, and practice drawing the graph by yourselves. And that brings us to the end of this lesson. My God, it has been long. I am not sure of the time because I record it in segments, but I bet we have hit the 2-hour mark. Anyways, show your appreciation by liking, sharing, and positive feedback. And I'm going to see you in our next lesson where we are going to handle mock papers, right? Yeah. See you then.